In today's video, we're going to be looking at section 11.4, which looks at testing hypotheses, this time about a population proportion. If you remember back to 11.2, we were dealing with hypotheses and testing hypotheses that dealt with a population mean. So you always had a null hypothesis that said that the population mean equaled something, and then you had an alternative hypothesis that stated that the mean was actually different than, less than, or greater than what you thought that initial value was. Okay. This time we're dealing with proportions. So it's very much the same thing, but this time you're going to have the null and alternative hypotheses are going to be about a population proportion. So they're going to say, okay, I think that my population proportion is equal to a certain value, but my alternative hypothesis says that it's going to be not equal to, less than, or greater than that value. Okay, and it's all based on the fact that they thought that their population proportion equaled a certain thing, but they've got some sample data that had suggested something else, so now they need to test this. Okay, so it's very much the same as what we have done before. So you're always going to end up with these hypotheses. You're going to have your null hypothesis, which is going to say that your population proportion equals some value. We'll call it P0, okay? It'll be whatever value they think it is, and it's always as a decimal. So if they ever give it to you as a percentage, make sure you go back and put it as a decimal, okay? And then your alternative hypothesis is going to state that the population proportion is actually either not equal to, greater than, or less than what you initially thought it was. Okay, so it all depends on what the problem says, as always. So you could end up with a two-sided alternative or a one-sided alternative, whether that be left-tailed or right-tailed. Okay. So it's very much the same as what we've done before. We're just now dealing with proportions. A couple of things to be aware of. It's going to have the same step-by-step process as we had before. And again, I'm going to do it the long way and then show you the short way on the calculator. In order to do this, if you remember, when we did the population means and we were doing these hypotheses with population means, you had to make sure that either your population was normally distributed or you took a sample size that was greater than 30. That allowed you to take that test statistic, which was a Z transformation of sample means, because you had to make sure that your sample means were normally distributed. Okay, and in order for your sample means to be normally distributed, you either needed to have a population that was normally distributed, or you had to take a sample size that was large enough, and we always said it had to be greater than 30. So you had to have one of those two things in order to do this. Now when you do this, okay, something that you have to be aware of, and we did cover this when we did proportions at the start, okay, a few chapters back, you have to either have that your sample size times that population proportion value is greater than or equal to 10, and you have to have that the sample size times the proportion of people that don't have that characteristic, so it's 1 minus P0, okay, P0 is the proportion of people that have the characteristic, 1 minus P0 would be the proportion of people that don't have the characteristic. Multiply that by the sample size, and that also has to be greater than or equal to 10. What this basically ensures is that your sample size is large enough. So as we had before when we dealt with means, we either had to have a normally distributed population or you had to have a sample size that was at least 30. Now we have these two conditions when we deal with proportions instead of means, okay? You shouldn't have to worry about this too much. They don't tend to bring this up. It's just something to be aware of, okay? But what this allows you to do, okay, these two conditions, it allows you to say that the sample proportions are normally distributed. And that allows you to take that Z transformation where you deal with the sample proportions, because your sample proportions are now normally distributed, which therefore means you can get your test statistic, which is the Z transformation. So this means that your sample proportions are normally distributed. Which means that you can now take a test statistic which is the Z transformation of sample proportions. So the Z transformation, or that test statistic, is Z is equal to P hat is your sample proportion. So when they do this hypothesis test, okay, they will say, well, I think that my population proportion is this, but I have taken a sample and my sample proportion was instead this. Your sample proportion that you have is P hat minus that population proportion value divided by the square root of your population proportion times 1 minus your population proportion over n. Okay, we did this before when we did the Z transformation with these sample proportions. Then you're going to go through your 5-step process as we did before. Okay, it's going to be very much the same as what we have done before. This time you're just dealing with proportions. And again, I'm going to go the long way with this, but you can also do it the shorter way. Okay, so the first thing that you do, okay, step 1, is you're going to determine the null and alternative hypotheses. Okay. Whenever you do your null and alternative hypothesis, always remember that your null hypothesis always suggests equality. So it's always suggesting that your population proportion equals the thing that you initially thought it was. And then based on what they say in the question, we'll determine what the alternative hypothesis is. So is it not equal to what you initially thought it was? Is it greater than or less than? Okay. Then step 2, you're going to state the significance level. So you're going to state what alpha is. Okay. Alpha is that significance level. It's the level at which they want to conduct the test. It's the proportion or the percentage of time that they want to reject that null hypothesis. So if you've got an alpha, the significance level equal to 0.05, you want to reject your null hypothesis 5% of the time, and you want to fail to reject it 95% of the time in that case. Okay. Step 3 is to find that test statistic. So step 3, find the test statistic. Okay. And that is what we've just said. So that's that Z score, that Z value that we just talked about, which is the Z transformation. And it looks very much like the last one. It's just that your standard deviation over the sample size, that looks slightly different this time. But it's very much the same as what we've done before. Then step 4 would be to find the critical value. Okay, and that's based on this significance level alpha. And then you're going to compare your test statistic to that critical value. And if that test statistic falls in that danger zone, exactly the same as last time, then you know that you're going to reject the null hypothesis. But if that test statistic instead falls in the region where we're okay with it, that means that we're going to fail to reject. So find the critical value and compare the test statistic to the critical value. Okay, and then step 5 is just to determine whether or not to reject that null hypothesis. Okay, so it's exactly the same as last time, it's just that your test statistic looks slightly different. Okay, that's the only difference here. You should notice that in your homework, it's split into 11.4a and 11.4b. 11.4a, they're expecting you to go this long way with it. 11.4b is where they introduce that p-value again, where you can compare p to alpha and decide whether to reject or fail to reject that null hypothesis. So it's very, very, very much the same, okay? But I'm going to tell you that short way just so that you have it, and then we're going to do an example. Okay. The short way again is you're going to get that p-value, and that p-value determines the probability that you have a test statistic that is at least as extreme as the test statistic that you calculate. Okay, so if that probability is less than alpha, It means that your test statistic falls in the danger zone, which means that you therefore have to reject your null hypothesis. So if you get a p-value that is less than alpha, you're going to reject your null hypothesis. But if your p-value is greater than that significance level, you fail to reject. And it's exactly the same reasoning that we had when I drew it back in 11.2. Okay, so if you're unsure as to what I'm talking about with these p-values, go back and watch the 11.2 videos, 11.2b, A, B, and C, I think it was. But go back and watch those just so that you can see what I'm talking about with these p-values, because it is exactly the same theory. Okay. But there is one slight difference. When you do this p-test on your calculator, it is very slightly different. If you go to stat and then across to tests on your calculator, so you go to stat and then go to tests. When we have been doing this so far, we have been doing z-tests and t-tests. Okay, when we are dealing with means and hypotheses that deal with means, we either do a z-test or a t-test. We did a z-test when we were dealing with hypotheses that were dealing with means, and you knew what that population standard deviation was. So you knew that sigma value. When you didn't know your population standard deviation, but you knew your sample standard deviation, okay, which is more like a real world problem, you'd do a t-test. Now we are dealing with proportions. So whenever you get one of these problems that wants to do a hypothesis test about proportions, what you're going to do is go to stat and go across to tests. Now before we've used z-tests and t-tests as we said, but now we want to go down to a one proportion z-test. You have just one proportion from one sample. Okay, so it's a one proportion z-test. It's going to ask you several things. First thing, it's going to look at p0. That is the proportion that they think this thing has. So the proportion of people or things in the population that have the characteristic. That's your population proportion that's in your hypotheses. Then, whenever you deal with samples, okay, so they'll tell you this is the proportion of things in the population that have the characteristic. But then they will probably tell you the proportion of things in the sample that have the characteristic. What this asks you is not for the sample proportion, but it actually asks you to split this up. So X is going to be the number of things in the sample that have the characteristic. So it's X is the number of things that have the characteristic in your sample, and N is the size of the sample. So you may have to do a calculation in order to find X. Sometimes they give it to you in Hawk, sometimes they don't. So they may say, hey, let's say 52% of the 100 people that we sampled had this characteristic. Well, in order to find what X is, the number of things that have the characteristic, you would have to do 0.52 times 100, okay? You can type that straight in to X, so you can do 0.52 multiplied 100, by which we know is 52. But make sure that X is actually the number of things that have the characteristic, not the proportion of things that have the characteristic in that sample, okay? So X is the number of things that have the characteristic. N is just the number of things in the sample. This line here corresponds to what you have in your hypotheses. So you either have a two-sided hypothesis test where it's a does not equal, you can have a less than, or you can have a greater than. And then when you go ahead and calculate, it's going to give you that test statistic Z. It's going to give you the p-value that we can go ahead and compare to our significance level to see if we want to reject or fail to reject. And it will also figure out for you what that sample proportion is. So it will actually figure out X over M and tell you the proportion of things in the sample that have the characteristic. It should match what you have in the problem if they have given you the sample proportion in the problem as opposed to the actual number of things in the sample that have that characteristic. Just as a heads up, for this part here, for X, the number of things that have the characteristic, sometimes you will do a particular problem where you have to figure out how many things actually have the characteristic in the sample.
So it would be the proportion of things in the sample that have that characteristic multiplied by the number of things in the sample. So like we said here, if it said that 52% out of the 100 people in the sample had this characteristic, in order to find x, you just do 0.52 multiplied by 100. However, sometimes you may do this and x may be a decimal, okay? So you may, let's say, I don't know, hopefully this comes out to a decimal. Let's say you had 82 people in your sample and 52% of them had a characteristic. So you're going to do 0.52 multiplied by 82. It comes out to a decimal. Your calculator does not like decimals, okay? What I would always do is round it up or down to the closest integer. What that will do is it will change the test statistic slightly, and it will change what your p-value is, again, only slightly. But in terms of whether you're going to reject or fail to reject the null hypothesis, it shouldn't change that p-value enough that when you compare it to alpha, it's going to be something completely different, okay? So what I would always do, if you end up with a decimal value, because your calculator will not run a 1 proportion z-test with a decimal, I would always round up or down to the closest integer, run it, and then when you get your z and your p-value, almost like, I mean, the z-value is going to be slightly off, so is the p-value, but you can use that p-value to still compare to alpha, and it should still tell you whether you're going to reject or fail to reject that null hypothesis, because it should be close enough to what the actual p-value would be that we're not really going to worry about it, and you can still compare it to that level of significance. But please bear that in mind. So if you do end up with a decimal value for x, you may have to go in and actually calculate your test statistic manually, like we did before, and not using this particular test in order to calculate it, okay? So if you get a particular problem and you go ahead and you do the 1 proportion z-test, but you get down to x and x ends up being a decimal value, but your problem is asking for a test statistic, so it's looking for that z-value, I would actually go ahead, come out of this and calculate that test statistic manually. You shouldn't have to do that many times. If you ever have to do that, it should only be once in your homework. I only ended up with 1 decimal x value in like the 8 problems through the homework. So it shouldn't happen very often, but you may very occasionally have to go ahead if you need a test statistic and this comes out to a decimal, you will have to calculate it manually by doing the sample proportion minus the population proportion over that square root that we had before when we calculated that z-value. So that is just a heads up. But if it's just asking whether you reject or fail to reject, you can still use the p-value that this would give you when you round that x value, because it should still be close enough to what the actual p-value is, where when you compare it to alpha, the significance level, it should still give you the same conclusion. So bear that in mind when you do these problems.
So I'll read out this example and I'll write down the major points. So it says the mayor of a town has proposed a plan for the annexation of a new community. From a sample of 900 voters, so n is equal to 900, our sample size, in the town, 53% favoured annexation. So the sample proportion, with the sample of 900 voters, they said 53% favoured the annexation. So your sample proportion would be 0.53. Okay. A political analyst wants to test the claim that more than 49% favour the annexation. So this political analyst has come along and said that normally you would get 49% would favour the annexation, but he wants to test whether more than 49% favour the annexation, because he's looked at what's happened in this sample and thought that something else is different. So his population proportion of what he thought it should be was 0.49. Okay, so this 0.49, that's your P0 value. That's what he thought it would be. But now he wants to test the claim that it is in fact more than that. Okay. Testing at the 0.01 level, so alpha is 0.01, is there enough evidence to support the analyst's claim? Okay. First thing, let's write out our null and alternative hypotheses so at least we know what we're testing. Okay, your null hypothesis is that the population proportion is equal to what they initially thought it would be, 0.49. Your alternative hypothesis is testing whether it is in fact greater than 0.49 because they've looked at this sample data and they've said, well, it's actually greater than, we want to test whether it is in fact greater than 0.49. Okay. Now, we know that alpha, if we went on to step 2, alpha is 0.01. So here what we have done, let's go back, we've done step 1, we've determined our null and alternative hypotheses. We've stated our significance level, okay? Then you could go ahead and find this test statistic, okay? I'm going to write this down, but you can go ahead and figure it out on a calculator. So this test statistic, okay? The test statistic is Z is equal to, it's the sample proportion minus the population proportion divided by the square root of the population proportion multiplied by 1 minus the population proportion over that sample size. Okay, you can go ahead and quickly figure that out. I can do that on a calculator very quickly. Okay, I get my Z value is 2.40. Okay, so that is my test statistic. Now what I want to do is figure out my critical value. Okay, we have here a right-tailed test. It is one-tailed and it is right-tailed because we have a greater than. So it means that our tail is going to be off to the right. And we have a significance level here of 0.01. So if you draw this out, because we've got a right-tailed test with a greater than in there, okay, my critical value, I'm going to call it Z1, okay, is going to be my critical value. I know that the area under the curve to the right is that significance level because I know it's right-tailed with a 0.01 significance level. Okay, so I know that 1% of the time is where I want to reject my null hypothesis. So my rejection zone, that danger zone, is going to be off to the right. Okay, that whole 1%. If I had a two-tailed test, so if I had a does not equals instead of a greater than here, that was a does not equals, I would have to split that 0.01 between the two tails. If it was a less than, I would have all of that 1% in the one tail over here. Okay, but right now I've got a right tail test because I've got a greater than in my alternative hypothesis, and so I've got my whole 0.01 area under the right side, okay, of that curve, which means that here I have 0.99, okay, to give me a total of 1 under the area of the curve. I want to find my critical value. So to find the critical value, we are looking at a Z-score, okay? Anything with proportions is always a Z-score, okay? Don't deal with T values here. We're always doing Z values. So to find a Z value, I always do inverse norm with my area under the curve to the left of the value with a mean of 0, standard deviation of 1 because I'm dealing with a Z value, okay? So when I go to, let me get this up on my calculator quickly. So I'm going to inverse norm, okay? My area is going to be 0.99. My mean is 0, standard deviation is 1 because I'm dealing with Z-scores, which means that I'm dealing with the standard normal distribution. When I figure that out, I get 2.326 roughly, okay? So that is my critical value. Now what I want to see is where my test statistic lies. So my test statistic was 2.40. 2.40 is around here, okay? That is where my test statistic was. It is to the right of it, which means it falls in this danger zone. So what does that mean? It means that my test statistic is within that rejection region. It means that I need to reject my null hypothesis. So as the test statistic so we reject our null hypothesis in favor of the alternative hypothesis. Okay, so that means that given what we had with our sample data, given that the sample told us that in fact 53% of people favoured the annexation, that tells us that the prediction for that population proportion was in fact not correct, and we actually have to go with this alternative hypothesis. So in fact, it tells us that because of what we found in the sample, the population proportion is actually greater than the 49% that they thought it would be. So to do this problem the short way, we're going to go to stat and across to tests, and I'm going to go down to a 1 proportion z-test. Then you have to input the data that we get, so we're going to input the statistics. P0 is the population proportion. It's the one that is in our hypothesis, so we know that that is 0.49. To get X, we know that the sample proportion was 53%, 0.53. So we know 53% out of our sample of 900 has the characteristic. So for X, you just do 0.53 multiplied by 900, and it will give you that X value. Okay, that's the number of people out of the 900 that have the characteristic. N is 900, the number of people in the sample, and then our hypotheses for our alternative hypothesis is a greater than. Okay, we want to see if the population proportion is actually greater than 0.49. We're going to go ahead and run it, and then we get for Z, this is our test statistic. So 2.40 is our test statistic. That's what we found before by doing it by hand. We did not have to round that X value in this case, so our test statistic is accurate and it matches what we got when we did it by hand. Then we get this P value here. That is what we compare to alpha, our significance level, to see whether we're going to reject or fail to reject our null hypothesis. Okay. In this case, 0.008 is less than alpha, so we're going to reject our null hypothesis. And then finally, p hat is 0.53. That was our sample proportion. It matches what we had. Okay. So the main thing to note from here is Z is your test statistics, the 2.40, which we found before, and then P is what we compare to alpha. If it's less than alpha, we reject our null hypothesis. If it's greater than alpha, we fail to reject our null hypothesis. So in this case, we are going to reject.